All right, here we go. Final part. It is qualitative circuit analysis. Okay, so suppose we have this circuit to the right. Suppose that resistance Z can be increased, or I guess it's increased, right? This is like a variable resistor. So I'm going to draw the arrow on it so we can show that it's being it's variable. Okay. Suppose that resistance Z is increased. What happens to the voltage drop in the current through W? Well, if you take one resistor and you increase its resistance, you're actually increasing the equivalent resistance. So Req increases, okay, meaning less current through the battery, right? Because if Req increases, you get less current because of Ohm's law, right? So that means less current. So more resistance means less current, okay, which means less current through W, okay, and that's because the battery and W are in series with each other. So if the current going through the battery decreases, then the current going through W decreases, okay, and then that also means less voltage through W, okay. Okay, and that's by Ohm's law, right? If resistance is the same and your current decreases, then your voltage overall will decrease. Okay. Um, what happens if what about X? Well, if you take a look, X is parallel to the YZ branch. And if you increase the resistance of Z, you're increasing the total resistance of that YZ branch, right? So more charges are actually going to want to go to X. So they'll go here and they'll either have to go to YZ or they'll need to go to X. More charges are going to go to X because there's less resistance here. They want to take the path of least resistance. So more charges go to X instead of the YZ branch. Okay. And if the wait, that which means there's more current. Okay. And therefore more voltage, okay, on the X resistor. Okay. Again, resistance is staying the same, so that's not having any effect on it. What happens to voltage drop and current through Y? Well, we've already discussed that more charges are going to go through X, so less are going to go through Y. Okay. So less charges go to the YZ branch, okay, because of increased resistance. Okay. So therefore, less current, which means less voltage through Y. Okay. Now, through Z, you can solve this two different ways. Maybe you recognize, okay, well, if resistance increases, then if resistance increases, then again the current is going to decrease. Is if the resistance increases though, then the voltage is going to have to increase as well. Well, wait, so does the current and the resistance decrease by the same factor? Is it going to cancel out? We don't know yet. But what we can figure out is the voltage drop. It may not be the same, but either way, if a charge goes from battery to W to Y to Z, it still needs to get rid of all of its voltage, right? So it's actually going to lose less voltage at Y. We've already said, right? Well, actually, we can kind of put it all together here, and I'll make it look all nice and formal. Okay, the voltage from the battery, okay, needs to wait. If you take that voltage and you subtract it from, or you subtract from it the voltage across W, then the voltage across Y, then the voltage across Z, okay, you should end up getting 0, right? Well, we've already seen that the voltage across the battery is going to stay the same. We're not doing anything with that. But the voltage across W is going to decrease. The voltage across Y is going to decrease. What has to happen to VZ to compensate for that? It would have to increase. Okay. So to put it into words, IZ decreases, and that's for the same reason that we cited earlier. Okay. but VZ must increase to balance. Okay. Suppose that a new resistance is connected in parallel to Z. Okay. So if there is so if we go back up to the circuit diagram, right, it's probably going to look something like this. We get another resistor in parallel to Z. Okay, right there. Let's call this resistor L. Okay. Um, so if we have resistor L now connected parallel to Z, that's going to change things, right? We're basically answering the exact same questions, but with that major change, okay? So it says, suppose a new resistance is connected in parallel to Z. What happens to voltage drop? Well, fun fact, if you have a resistor that gets connected in parallel, so if you add a resistor in parallel, you're actually going to decrease your equivalent resistance, right? So adding parallel resistors, okay, decreases equivalent resistance, okay? That's just because of how the math works out, right? So less Req means more current, which means more current through W and more voltage through W, okay? What about the voltage drop in current through X? Well, now that you have, so what's actually kind of changed is if you look at the circuit up here now, this additional resistor has actually effectively decreased the equivalent resistance of just the YZ branch, right? So the YZ branch, the effective resistance of it has decreased now because we added something in parallel. So when we calculate that, we would do 1 over the value of L, right? And that would actually decrease the equivalent resistance. Even though we did add a resistor, it would actually decrease the equivalent resistance, okay? So we would say less resistance in the YZ path. Okay. So more current is going to go through the YZ path, meaning that X is now going to be the path of more resistance. So more current goes YZ, so less IX and less VX. Okay. Okay. Now, what happens to the voltage drop in current through Y? Well, we've just said that more charges are going to go to the YZ branch for this reason that there's less resistance in the YZ path. So more current goes through YZ. Okay. So therefore, more current through Y, which would then give us more voltage through Y. Okay. More current through Y, and that gives us more voltage through Y. Okay, and the final part is what happens to voltage drop in current through Z? Well, Z, right, last time when we looked at the current, so Z would get the same, in the previous one without this extra resistor, Z would get the same current that Y had, except now it's not going to, because some of the current is going to split at the branch and go into resistor L and then come back around and join after resistor Z. So Z is not going to be getting the same current that it did. It's actually going to have less, maybe only by a little bit, maybe, but it will actually have less. Okay, so Z has less current since L splits charges. Okay, so less current through Z, which means less voltage through Z. Okay, and Z and L would have the same voltage because they're in parallel with each other. All right, that is qualitative circuit analysis. Short, sweet, simple. All right, make sure you hit that subscribe button. Thank you.